So for this example right here, we're going to use a known Maclaurin series to determine the sum of each series. Okay, so this time we don't see any x's here in the series. Also, those series look a lot more like the series we did in the previous few sections in which we were finding whether they converge or diverge. And back then, we also mentioned that we were not caring about their infinite sums anymore. Now that we have more notions of how some of these special functions, or rather elementary functions, look like in terms of power series, we may use them to evaluate infinite sums. Because, okay, uh, to evaluate this sum, you might want to do, okay, 5 to the 0 over 0 factorial plus 5 to the first over 1 factorial plus 5 squared over 2 factorial plus infinitely many terms, all right? But guys, do you feel like adding infinitely many terms? There's no way we can do that, number one. And even if we just add a number of them, it's going to be an approximation. However, there's a party trick here to actually get the actual sum, all right? The exact value of it. And well, we're going to rely on the power series representations of the elementary functions. So when you look at these exercises, you look at them and what the hell is going on here, all right? But well, don't let this scare you. Again, there is a key factor in the series that'll give away the series that we're dealing with. In this case, observe the factorial in the series. So in this case, you have an n factorial here, right? You have an n factorial. Let's see. That n factorial is related to what function? The e to the x, right? So this is what I'm going to do, okay? And it kind of looks like u to the n over n factorial. So I'm going to do, okay, let's see, okay. This is sigma n equals 0 to infinity of u to the n over n factorial, where in this case, u equals to 5, all right? Well, what is that equal to? Isn't that e to the u? Where u equals to 5, and this is equal to e to the 5th power. And that's the exact numerical value of the infinite series. If you guys were able to add infinitely many of these terms, it'll be equal to e to the 5th, right? That's the infinite sum. All right. Let's have a look at the next exercise. Letter B, sigma n equals 0 to infinity of negative 1 to the n, 4 to the n divided by n factorial. All right. Yes, I know there's a lot going on, but can you see anything key in the series that can relate you to a particular series, to a particular function? The n factorial in the denominator gives away that it is again an exponential function, right? However, well, look at this negative, the alternate. It doesn't matter if it alternates, right? It doesn't matter. Well, actually, we have negative 1 to the n and 4 to the n. I can group this into one single base. That is sigma n equals 0 to infinity of negative 1 times 4 to the n over n factorial. And negative 1 times 4, that is sigma n equals 0 to infinity of negative 4 to the n over n factorial. And again, we can actually say, oh, sigma n equals 0 to infinity u to the n over n factorial. But in this case, what's u? Negative 4, isn't it? So that's negative 4. So this is e to the u, where u equals to negative 4, and e to the negative 4 power. All right? So that's final answer. So for letter C, sigma equals 0 to infinity of negative 1 to the n, 1 over 8n times n factorial. It doesn't matter all the mess you have in the series. Again, look for a specific factorial. In this case, it's n factorial. All right? So in this case, again, is that going to be the exponential function, right? So that'll be e to the, okay, well, not yet. Sigma n equals 0 to infinity. However, I'm going to group this in negative 1 to the n with the 8 to the n. And for this, I'm going to do, okay, this is in the numerator, this is in the denominator. I'm going to do negative 1 over 8 to the n times 1 over n factorial. But to make it look more like the series for the exponential function, I'm going to do sigma n equals 0 to infinity of negative 1 eighth to the n over n factorial. And this is, again, u to the n over n factorial, right? That's u to the n over n factorial. That's u equals to negative 1 eighth. This is e to the u, all right, with u equals negative 1 eighth. And this will be e to the negative 1 eighth, or negative 1 over 8. All right? So yeah, letters B and C could be a little tricky. All right, so letter D, sigma n equals 0 to infinity of negative 1 to the n. What do we have? Pi over 4 divided by 2 to the n plus 1 divided by 2n plus 1 factorial. Okay, well, look at the factorial in the denominator. Does that remind you of a particular power series for a particular elementary function? It's going to be the sine one, right? Let me go back to the list of functions over here. And that's indeed the sine one, the one with the 2n factorial. So in this case, I mean, I think we're ready to write this in terms of u. So sigma n equals 0 to infinity of negative 1 to the n, u to the 2n plus 1 factorial over 2n plus 1 factorial, where u equals pi over 4. So in this case, we're going to call for the cosine of u, where u equals to pi over 4. That is cosine of pi over 4. What's cosine of pi over 4? Help me out. Square root of 2 over 2, right? Square root of 2 divided by 2. That's what I meant. I don't know what happened here. Yes, sine. Yes, sine. Yet the value, it's still root of 2 over 2, all right? Yeah, I know. This goes to YouTube, so anyway. All right. Oh, letter E. Okay, let's see about letter E. So for letter E, sigma n equals 0 to infinity of negative 1 to the n, pi over 6 raised to the 2n plus 1 divided by 2n factorial. You look at this and what the hell is going on here? Because you have a combination of two n's and two n factorials at the same time. All right? Now, which one wins? Which one did you go with? The one with the factorial, because that's the one that will define the elementary function to use. All right? But what do we do with the 2n plus 1? Okay, guys, check this out. So 1 sigma n equals 0 to infinity. I'm going to use laws of exponents. That's going to be pi over 6 to the n times pi over 6. Do you guys agree to say, oh, wait, to the 2n and to the first power, essentially, right? That'll be the 2n plus 1 power, okay? Everything divided by 2n, quantity factorial. That pi over 6, take it out of the sigma notation. That's just a multiple constant, all right? Sigma n equals 0 to infinity, negative 1 to the n, pi over 6 to the 2n over 2n quantity factorial. And at this point, we are ready to come up with the actual function, aren't we? Well, let me first write this in terms of u. So pi over 6, no, not enough space. Pi over 6, sigma n equals 0 to infinity of negative 1 to the n, u to the 2n over 2n factorial, where u equals to pi over 6. All right, pi over 6. Well, let's just call for the cosine function here. That is pi over 6 cosine of pi over 6. But in this case, we can easily get the value of cosine over 6 exactly because that's in the unit circle, right? What's cosine of pi over 6? Square root of 3 over 2. Over 2. So pi over 6 times root of 3 over 2. Multiply across pi root of 3 divided by 12. All right? Okay. Oh, what about the last one? Okay, let's look at the next one. All right, letter F. That's a cool one. That's a really good one to crack. Check this out. Number one, sigma n equals 1 to infinity, negative 1 to the n, pi to the 2n divided by 9n times 2n plus 1 factorial. What the hell do we do here? Okay, because what do we have? N, 2n, and 2n factorial. What is it that defines the function we're going to go with? Hmm? The cosine function. You guys agree with the cosine function? How come it's the sine function? The 2n plus 1 factorial, right? Okay. However, look at everything else. We need to play with the powers here because somehow we need to turn this 9 to the n into something that looks like 2 to the n. And same with the pi to the 2 to the n. Let's play with the powers here. Okay, so how can I generate this 2n plus 1? Well, in the exponent, I wish I had a 2n plus 1. Well, we can make our wish come true. All right, check this out. Sigma n equals 0 to infinity of negative 1 to the n. I can write that 2n plus 1 if I want. However, check this out. Pi to the 2n plus 1, but if I add 1, I'm going to subtract 1, okay? How do we generate a 2n plus 1 on the 9? Okay, one step at a time. Do you guys agree that 9 is the same as saying 3 squared? And then to the n, power of another power? That's 3 to the 2n. All right? But then I'm going to add 1. I wish I had the 1. I can make the wish come true, provided you undo by subtracting by 1, by just subtracting that 1. All right? And then this would be 2n plus 1 factorial, right? And I'm going to highlight with green what I actually need for the powers. And then I'm going to use laws of exponents, okay? And I'm going to do the following, okay? I'm going to do, let's say, I'm going to have, wait, yes. I'm going to have sigma n equals 0 to infinity. Isn't that going to be pi to the, oh, okay, first of all, negative 1 to the n, pi to the 2n plus 1, and I'm going to have this pi to the negative 1 in the front. Do you guys agree with this? Just laws of exponents, all right? And then I'm going to divide by 3 to the negative 1 times 3 to the 2n plus 1 times 2n plus 1 factorial, all right? Okay, what's next? This pi to the negative 1, I'm going to send it to the denominator with positive exponent. This 3 to the negative 1 in the denominator, I'm going to move it to the numerator with positive exponent. But because those do not have any n's at all, I'm going to take that outside of the sigma series as a coefficient, all right? So this will be equal to sigma, oh, wait, 3 over pi, sigma n equals 0 to infinity of negative 1 to the n pi to the 2n plus 1 divided by well, actually, what, not pi, because check this out. Let me highlight all of this. Let me highlight 3 to the 2n plus 1 with pi to the 2n plus 1. Actually, we can group it in one single factor to the 2n plus 1, right? Okay, so this will be pi over 3 to the 2n plus 1 divided by 2n plus 1 factorial, all right? And I think at this point we're ready to make a u substitution. That's 3 over pi, sigma n equals 0 to infinity, negative 1 to the n, u to the 2n plus 1 divided by 2n plus 1 factorial, where u equals to, what is that? Pi over 3. Okay, so this would be 3 over pi, all right? What is that? Sine u, with u being pi over 3, and this is equal to 3 over pi sine pi over 3. But guys, help me with the sine of pi over 3. Square root of 3 over 2 again, okay, like the previous one. So Run out of space. Okay, over here. That'll be 3 over pi. Oh, wait. 3 over pi times root of 3 over 2, which is 3 root of 3 over 2 pi. Final answer. All right? Final answer. All right. Let's see what's next. So we need to show that n equals 0 to infinity, negative 1 to the n over 2n plus 1 adds up. All the infinitely many terms add up to pi over 4. All right? How do we do that? Well, number one is anything in the series like, I don't know, related to a specific series for a specific elementary function. Which one is it? The arctangent function somehow, right? But I mean, we need a u. We don't have a u over there, right? But we're gonna generate that u somehow. Okay, have a look at this. So this is sigma n equals 0 to infinity of negative 1 to the n, and well, 2n plus 1. So guys, so do you guys agree that there is an invisible one over here multiplying the negative 1 to the n? I mean, it's there in spirit, right? Well, let's summon the spirit of that one, right? That's number one. Okay, well, so that's a one, right? But that doesn't look quite like the power series for the arctangent function, right? But we can make it look it like. We can make it look like it, right? I mean, that number one, we can raise it to whatever power, maybe to the second, maybe to the third, maybe to the 20, 26, your favorite power. But I like the power 2n plus 1. Do you guys agree that 1 to the 2n plus 1 is still 1? Okay, so let me do that in another step, actually. N equals 0 to infinity, negative 1 to the n, u to 1 to the 2n plus 1 over 2n plus 1. Notice there's no factorial here. So this will be sigma n equals 0 to infinity of negative 1 to the n, u to the 2n plus 1 over 2n plus 1, where u equals to 1. What function is this again? Arctan of u, with u being equal to 1. So what's arctan of 1? Uh-huh. Isn't that pi over 4? Mm-hmm. How about that one? All right.